Hi, everyone, and welcome. Ever stop to think about the hidden gears turning behind your everyday internet use?
Probably not often. It usually just works.
Exactly. So today we're doing a deep dive into TCP/IP. It's basically the invisible framework that makes sure all your digital stuff gets from A to B reliably.
Hmm.
We're using a pretty comprehensive report to help us unpack it all.
Have a good
So
one.
TCP/IP, people often say it like it's one single thing, right? But it's actually a suite, a collection of rules.
That's right. It's not monolithic. Think of it as a team of protocols working together.
Okay, and the main goal.
The big picture is reliable, end-to-end data transmission, making sure what you send is what gets received, intact.
And where did this all start? I hear it has quite a history.
It does. It goes back to the 1970s, believe it or not. Started with the U.S. Department of Defense.
Ah, the ARPANET days.
Precisely. Vint Cerf and Bob Kahn first proposed a single transmission control program back in '74. But the really crucial step, the game changer, was splitting it up, separating it into distinct protocols like TCP and IP.
Why was splitting it so important?
Modularity. It made the whole system much more robust, more flexible. You could update or add things, like IPv6 later on, without having to redo the entire foundation.
Ah, I see. So it wasn't just about building a network, but one that could actually evolve. Future-proofing, kind of.
Exactly. That design choice was key to the Internet's growth.
And for you listening, this underlying structure is why almost everything you do online, browsing, email, streaming, you name it, just works. It's that seamless, invisible infrastructure.
And to manage all this, TCP/IP uses a layered model, 4 main layers.
Right, the layers. Let's break those down.
Okay, you've got the application layer at the top. That's where your apps like browsers live, using protocols like HTTP.
Mm-hmm.
Then transport, with TCP and UDP, deciding how data gets sent reliably or quickly.
Okay.
Below that, the internet layer, which is IP's job figuring out the path across networks.
The addressing part.
Yes. And finally, the network access layer, dealing with the physical connection, like Ethernet or Wi-Fi.
So data starts at the top, say, in my browser. How does it actually move through these layers? It's not just handed off, is it?
No, there's a process called encapsulation. Think of it like packing a box and adding labels.
Okay.
As your data goes down each layer, that layer wraps it with its own specific info headers, sometimes trailers, like adding an address label, then maybe postage info.
Got it. Layer by layer, adding instructions.
Exactly, preparing it for the journey across the network.
And then when it arrives at the other end.
The reverse happens, decapsulation. Each layer on the receiving end strips off its corresponding label or header.
Unpacking the box.
Precisely. Checking things off, ensuring the data's integrity, and passing the core data up to the next layer until it reaches the application.
And this layering also helps with security, I imagine.
Absolutely. Security can be applied and checked at different layers along the way.
Let's zoom in on IP then, the Internet Protocol. You called it the addressing layer, like the Internet's postal service.
That's a great analogy, yeah. IP handles the logical addressing, giving every device a unique IP address and then routing the data packets or datagrams towards their destination.
And these addresses, we hear about IPv4 and IPv6. What's the difference there?
So IPv4 uses 32-bit addresses. That gives about 4.3 billion unique addresses. Sounds like a lot, but we've basically run out.
Right, IP address exhaustion.
Exactly. So IPv6 is the successor. It uses 128-bit addresses. The number is astronomical. Something like 340 undecillion. More addresses than we'll ever realistically need.
Enough for every toaster and toothbrush.
Pretty much. And we also have public IPs, which are globally unique, versus private IPs used inside your home or office network.
And IP can send data in different ways too, right? Not just one-to-one.
Correct. There's unicast, the standard one-to-one delivery.
My computer to a website server.
Yep. Then multicast, which is one-to-many, sending to a specific group that's subscribed. Think certain types of video streams.
Okay.
And anycast, which is one-to-one of many. It sends your packet to the nearest server out of a group, which is often used for things like DNS for speed.
Okay, so IP gets the packet addressed and routed, but it's best effort, isn't it? No guarantees.
That's right. IP itself doesn't guarantee delivery or order or check for errors. That's where TCP comes in.
Ah, the other half of the duo, transmission control protocol, the quality control layer.
Exactly. TCP sits on top of IP at the transport layer and adds the reliability. It ensures data arrives correctly, in order, and error checked.
How does it manage that, starting with setting up a connection?
It uses what's called the three-way handshake. It's a quick back and forth. SYN, SYN, ACK, ACK.
Synchronize, acknowledge.
Right. establishes a reliable connection before any actual data flows. And then there's a similar four-way handshake to close the connection cleanly when you're done.
And the reliability part during the transfer.
Several key things. Sequence numbers to make sure packets get reassembled in the correct order. Acknowledgements, or ACKs, where the receiver confirms which packets it got.
So the sender knows it arrived.
Yes. Checksums to detect if any data got corrupted in transit. And crucially, retransmission. If the sender doesn't get an ACK for a packet, it assumes it was lost and sends it again.
Wow. Okay. So it turns IP's send and hope into a guaranteed delivery service.
Pretty much. It adds overhead, but ensures that reliability.
But that overhead makes it slower, which is why we sometimes need something else, like UDP.
Exactly. Not every application needs TCP's level of, well, meticulousness. User Datagram Protocol, UDP, is the alternative at the transport layer.
So TCP versus UDP, what's the main trade-off?
TCP is connection-oriented, meaning it sets up that formal connection. It's reliable, ordered, error-checked, but all that management adds overhead and makes it a bit slower.
Right.
UDP is connectionless. It just sends the packets. It's best effort, like IP, much faster, very little overhead, but no guarantee of delivery or order.
So for you, the listener, when would you use one over the other?
Well, think about what you're doing.
Okay, so for web browsing or email or downloading a file, you need every single piece of data, right, in the right order.
Absolutely. Missing data would corrupt the file or make the web page garbled. So that's perfect for TCP. You need that reliability.
But what about, say, a live video call or online gaming?
There, speed is often more critical than catching every single packet. A tiny glitch or dropped frame in a video stream is often less disruptive than a long pause while TCP retransmits lost data.
Right, you'd rather have a tiny visual hiccup than the whole stream freezing.
Exactly. So for applications like live streaming, VoIP, online games, UDP is often the better choice. Speed and low latency trump absolute reliability, and the application might handle minor losses itself.
It really shows the power of having both tools available.
It does.
So, wrapping up, it's this incredible partnership, isn't it? TCP and IP. IP figures out where to send the data packets across the vast internet.
Handling the addressing and routing.
And TCP rides on top, ensuring how that data arrives reliably, in order, and complete.
The where and the how working together.
People sometimes call it the hourglass model, right? With IP as that narrow waist. Lots of different applications above, lots of different network technologies below, but IP connects them all.
That's a great way to visualize it. It allowed the internet to scale massively because IP provided that universal interconnection point.
It's truly elegant, and the fact that TCP/IP was developed as an open standard really fueled global innovation and connectivity in ways that are just staggering.
Undeniably.
So here's a final thought for you. Given how fundamental, how pervasive, yet how invisible TCP/IP is, what does this kind of enduring, adaptable, technical brilliance tell us about building the foundations for our increasingly digital future? Something to ponder. Thanks for joining our deep dive today.